All right, so today we're gonna start the lecture 2, talking about renormalized perturbation theory, part 1. So I'm gonna review very briefly, as usual, the previous lecture, lecture 1. And if there are any questions at any point, please do ask. I will review it a little bit differently, highlighting some other aspects of dimensional counting. So what we did last time was dimensional power counting. Now, let's start by talking about scaling transformations. So what is a scaling transformation or dilatation? It's when x mu is sent to x mu over lambda, or you could think of it as some new, in the passive language, that's active. In the passive language, you could think of x prime mu is x mu over lambda. It's just a new set of coordinates, new set of rulers. Under this transformation, the volume measure, this is a space-time volume. These space-time in this part 2 of the course. I don't quite recall actually whether I used little d for space or space-time last time, but here and onwards, going up forward, d is going to be space-time. So the volume form will transform like 1 over lambda to the power of d. So Lagrangian is dimensionless, because we are working in dimensions where h bar is 1. And if you recall, we had the path integral measure was e to the power of I action over h bar. If action is, if h bar is dimensionless, s has to be dimensionless as well. Action has to be dimensionless as well. This means that the Lagrangian density should have dimension d, space-time, mass dimension d. Right? This is mass dimension. All right, so consider a free scalar field. It's the Lagrangian is half del phi squared minus half m squared phi squared. This is a mass term and some arbitrary interaction term in these space-time dimensions. From the first term, are there any questions? Okay, if there are questions, do ask, please, at anyone. From the first term, the kinetic term, you know that because this term should have dimension d, and every derivative has mass dimension 1, the mass dimension of phi is d minus 2 over 2. So it means that under scaling transformation, phi of x becomes phi prime of lambda minus 1 of x, or lambda, which is lambda to the power of d minus 2 over 2 phi of x, right? So it's a scaling field. M squared, of course, has dimension 2, and the Gn, which is, so I'm writing a generic polynomial, which is analytic, so I can expand it in a series expansion, and Gn term will have dimension d minus n times d minus 2 over 2, right? This is a coefficient of the nth power in the polynomial. When m is 0 and all Gn are 0, meaning that when you only have the kinetic term, you have a theory of massless free boson scalar field. Then x going to x over lambda is a symmetry. Is that part clear? Well, we check it explicitly, which means that the action for m equals 0 and Gn equals 0 for all n is the same as, remains the same under scaling transformation. This theory is a scaling variant, massless free theory. Now, Wigner's theorem, if you recall from part 1 of the course, tells you that there exists a unitary representation of this symmetry group. The group is R. Scaling is R because lambda belongs to R. So which means that what acts on phi of x is this unitary transformation, e to the power minus I d R. D is the generator of the group R, which is it's a trivial Lie algebra, right? It's a dilatation operator, not to be put a hat so they don't confuse it with the superficial degree of divergence that we talked about last time, but we also denoted it as capital D. So what's actually happening is if you apply this unitary transformation to field phi x, it will pick up this lambda to the power of d minus 2 over 2. This is the active picture, right? This is where we actively scale. Now, this is the case, well, in the presence of other terms, spoil the symmetry, right? So you're not guaranteed when there are other terms, you do not have scaling variance, you do not have a symmetry, and you're not guaranteed that there exists such an operator. So this relation is specific to the massless free theory. In the presence of other terms, the presence of other terms spoils the symmetry. And if you were classically to recover the symmetry, Gn will have to transform also with a canonical power dimension, right? Which is this. All right, any questions? Good. So let's talk a little bit more about other theories. So we just found an example of a classically scaling invariant theory, right? We'll see in a bit. There was a question about this last time. This massless free scalar is classically scale invariant. It's relativistic invariant, and it's actually conformal invariant. And we'll see that in a little bit why that follows. I'll repeat the analysis that we had in part 1 of QFT that mentioned that classically. Quantum mechanically, of course, this could fail due to what is the phenomenon that's called anomaly, where when the measure of the path integral is not invariant under the symmetry. We'll get to that in this course at some point. We'll discuss this in detail. We're not dealing with anomaly for now. What I need you guys to understand is that, well, one thing that you need to know for now is that free field theory, this free massless scalar, is classically and quantum mechanically scale invariant. So it's actually conformal field theory. All right, so let's pick another example. So here's a Lagrangian, the classical, the Lagrangian density, psi bar del psi minus, so there's a fermion, right? Psi bar del psi is the kinetic term for the fermion, minus m psi bar psi, this is a mass term for the fermion, minus some coupling, gy of phi psi bar psi. Oh, actually, I totally forgot. So this is a scalar term. So there is also a scalar kinetic term as well. Depending on how I put the sign, I don't quite recall. Whoops. All right. So this is a Yukawa interaction, right? So the Yukawa theory has a free scalar field and a fermion, and there's this interaction. Here we're giving mass to the fermion, and also we're considering psi bar psi squared. This is a 4-point interaction for the fermion. We haven't discussed that so far in this course, but this in part 1 of the course, but this action classically is called the Yukawa theory model, right? This is the action. Now, of course, the dimensionality of phi is still as before, d minus 2 over 2. The dimensionality of psi is d minus 1 over 2 because the kinetic term for psi has only one derivative. We talked about that in detail last time, right? In QFT1. So this means that the dimensionality of g of y, the Yukawa theorem, is 4 minus d over 2. And the dimensionality of h is 2 minus d, right? So an interesting observation here is that the theory that has the theory in 4 dimensions, 4 space-time dimensions, if it only has gy and h is 0, is classically invariant, scale invariant. Sorry, you should disallow the mass term. So if you just take psi bar psi and this term plus the kinetic term, that would be classically scale invariant in 4 space-time dimensions. Now, if you exclude these terms and only consider this term is classically invariant in 2 space-time dimensions. The reason I mentioned that is that also plays an important role. Okay. Now, what we're seeing here is that the scale invariance occurs when the coupling constants are dimensionless, right? Now, we also saw in the previous lecture that when the coupling constant is dimensionless, from superficial dimensional counting, this was a signature of what we call the renormalizability, right? So at this point, there is a connection that we find at the level of classical analysis between what we call between classical scaling variance and renormalizability. Good. So lambda, okay, is that good? This is very, very high level, and there's no. This has to be. We have to discuss this in more detail. There's no. It's very nuanced and complex, but this part of the course is going to be all about this. We call the couplings, the terms in the Hamiltonian that have dimensionless couplings, as the relevant. Sorry, marginal. Sorry, my bad. Marginal terms, right? So remember that. We use this terminology, right? I think I did use relevant, irrelevant, marginal. Well, if I didn't, I'll get back to that and repeat it. All right. Any questions about the Yukawa theorem model? So this action gives you examples where you get scaling variance in D equal to space-time, two space-time dimensions, or 4 space-time dimensions, depending on what values you pick. Good? Questions? All right. Now, let's talk about another theory. This theory is a theory of gauge fields. So the action looks like del A squared. Sorry, let me remind you what the action is. So take it to be QED. We haven't talked about QCD. This comment is from the last year when I actually explained QCD in part 1 of the course, but it doesn't matter for now. So here the Lagrangian density, if you recall, this is a QED, is this, and F mu nu is del mu A nu minus del mu A mu. So from the point of view of dimension counting, Lagrangian density is del A squared. That should have dimension space-time dimension D, which means that A mu has dimension D minus 2 over 2. Good. Now, is that good? There is a covariant derivative. Did we define covariant derivative in part 1 of the course? Well, it doesn't matter. I think we did, but if you don't recall, so there's covariant derivative, which is del mu minus IG A mu. This involves adding 2 terms, del mu and IG A mu. This G is the electron, is a coupling constant of QED. It's the electron charge, right? This tells us that the dimensionality of G and A should be related, right? So dimensionality of A is 1 minus G, which means that from this equation, putting these two together, you find that G squared should have dimensionality of 4 minus D. So once again, you find that gauge theory in 4 space-time dimensions is scaling variant because the dimensionality of the coupling, because the coupling is dimensionless. Good? Question? So for example, QCD, quantum chromodynamics, this is a particular gauge theory we'll talk a lot about in this course, is classically scaling variant, but quantum mechanically is not. This is not the case of anomaly. It's a more complicated phenomenon. It's called dimensional transmutation, and we'll talk about that in this course in detail. Questions? I think, yeah, I think we did not discuss this. Sorry. I think I have not described this covariant derivative or this discussion in detail. We'll come back to this. So that was all about what we discussed last time. Today we're going to talk about conformal symmetry a little bit. we talked about modern view of quantum field theory, and we talked about renormalized perturbation theory. So we'll start the discussion of renormalized perturbation theory. So before I start, are there any questions? Yeah, I realized that I have not described non-abelian gauge theory. So the example of QCD, if you're unfamiliar with it, because I've not explained it, and I'll explain in the next part of the course. Question? The theory that's scale invariant is, well, okay, sorry. I'll not comment on this. Of course, classical QED is not scale invariant because fermions have masses. I'll just leave that comment so to avoid confusion. If you don't have masses, then you have scale invariance. All right. Good.
Professor, I have a question.
Yes.
In the gauge fields case, I think you mentioned that in dimension 4, it's because the action is scale invariant, so that means we only have to let the coupling constant to have 0 dimension. Is that right?
Has no dimension. It's dimensionless. Coupling constant is just a constant. Yes.
Yeah.
The number.
But in the previous example, like in the Yukawa model and the scalar field, we have to let the coupling constant vanish, so we can get the scalar invariance.
No. Sorry. Here, the coupling. So in D space-time equal to 4, the coupling constants of GY doesn't have to vanish. The coupling constant GY does not have to vanish. What should vanish is dimension. So it has to be dimensionless.
Yeah.
Right?
Yeah.
But these guys should vanish, of course, because in D equal 4, they do not become dimensionless.
Okay.
Right? So the theory that scale invariant is M equal in 4 dimensions, has M equals 0, GY anything, H equals 0. Another theory that's scale invariant is M equals 0, GY equals 0, H anything in 2 space-time dimensions.
Yeah. Got it.
Good?
Yeah.
Okay. Any other questions? We will talk about 2 space-time dimensions and 4 space-time dimensions a lot later in the course in the context of non-abelian, in the context of nonlinear sigma models, but as explicit, sensible models of quantum field theory. All right. Let's get started with this lecture. At any point, if there are any questions, stop me. Okay, so let's recall the space-time. So conformal transformations are space-time transformations. So we're not dealing with internal symmetries. We're talking about space-time symmetries. So what's the Poincare group? These are the isometries of flat space-time, Minkowski space-time. They're generated by translations and Lorentz transformations. Okay, so the Lorentz transformation corresponds to the group SOD minus 1, 1. It's actually, if you recall, it's OD minus 1, 1, and then there's a special part that has to do with the determinant, because in even dimensions, there are 4 disconnected parts. So you talk about SO plus D minus 1, 1 in even dimensions, and in odd space-time dimensions, you talk about SO of D minus 1, 1, because there are 2 disjoint parts. So the connected piece is in even dimensions is SO plus D minus 1, 1. The full thing is OD minus 1, 1, right? And the parity in time, or the discrete transformation that we're taking in between these guys. There's a covering group. We talked about this. The covering group is spin D minus 1, 1. Let me just put the plus here so that I'm going to pretend I'm working in even dimensions. Spin plus D minus 1, 1. This is if you're not talking about the 1 plus 1 dimensions, this is the double cover. This is the double cover of SO plus, and it allows for the existence of fermions. Fermions are things that you go around by 2 pi and pick up a minus sign. Conformal group is larger. So in addition to these Poincare transformations, it has dilatations, this transformation. It has special conformal transformations, which is x mu over x squared going to x mu over x squared plus by. This is perhaps a compact way and useful way of memorizing or thinking about special conformal transformations. So this way of writing the special conformal transformations tells you right away that there's a simple way of thinking about how to get the conformal group. If you have the Poincare group and you add to it dilatation, you do not quite yet have conformal group. If you have inversion as a symmetry, then inversion, translation, and inversion back will give you special conformal transformations. So think about, are there scale invariant non-conformal theories? I'm going to comment on this a little bit later in a bit. Clear? Is that clear? The simplest example of this is, what is the simplest example of this? Let's see, 0 plus 1 dimensions. Yeah, but that's not even. Well, okay. So let me not confuse you guys. Do I want to comment on that? Well, let me just say it for those of you guys who can want to think about this. So 0 plus 1 dimensions, what we have is translations. That's all we have. There's no Poincare transformation. There's no Lorentz transformations. Then we have dilatations, and dilatations and translations will generate the group T going to AT plus B. The analog of inversion is T going to minus 1 over T, putting these two together, which is an inversion, translation, inversion back, will give you, as a symmetry, will give you a special conformal transformation. If you put all of these together, you get this as a symmetry. Does anyone know what the name of these transformations are for real variables A, B, C, D? This is the conformal group in 0 plus 1 dimensions. That's the
Mobius?
Sorry?
Mobius transformations?
Mobius transformations, exactly. It's PSL2R. Correct. It's Mobius transformation. That's a conformal group in 0 plus 1 dimensions. All right. Good. Perhaps less in this relation is often written this way. This is equivalent to writing it this way. I wrote it this way so that to make the role of inversions clear. But this could be equivalently written this way. This is usually the usual form that we find in most textbooks. Now, infinitesimal special conformal transformation will have a generator, which is this. So you could just write down an infinitesimal transformation. What it will have is this generator. So it's a simple exercise to see that another way of defining conformal transformations is through the following observation, that all these transformations that I define have the property that they send the metric to the metric multiplied by a smooth, non-vanishing real function. Right? So under diffeomorphisms like the one that I've discussed, G mu nu goes to this. Right? This is the transformation of the metric under diffeomorphism. And if you require that this is just a function of x that is smooth, non-vanishing, and real, you immediately learn that, sorry, you could show that these transformations will have the property that once you plug them inside this factor becomes some smooth non-vanishing real function. And also it goes the other way around. All the functions, all the diffeomorphisms that transform the metric in this way could be always repackaged this way in these space-time dimensions larger than 1 plus 1. 1 plus 1 is an exceptional case. And these are called conformal transformations. This is one other way of defining conformal transformation. Lorentzian conformal group is SOD, 2 in these space-time dimensions. In these space-time dimensions, the Lorentz group is SOD minus 1, 1 that sits inside this. So do think about why the conformal group is SO2 D, 2. So in the example that I just gave you, 0 plus 1 dimensional conformal group, I said it's the Mobius transformations, PSL2R. And what is this? This is SO1, 2. There's a plus here, actually. SO1, 2 in 0 plus 1 dimensions. SO1, 2 is the same thing as PSL2R. It's the same thing as PSU1, 1 as well, in case you know what that group is. It's the same thing. All right, questions? Well, you do know what PSU, 1, PSU1, 1 is, but I've defined this in part 1 of the course. Questions about this? Okay. Now, a quick reminder of why we talk about conformal transform, why scaling and relativity give you the full conformal group. Classical argument for it. This is not a quantum argument, right? Consider the stress tensor, theta mu nu. Sometimes people write it as T mu nu, but I'm just sticking with the notation I was using in the part 1 of the course, theta mu nu. It's the conserved current for Poincare transformations. So we saw in part 1 of the course from Noether theorem, every time you have a symmetry transformations, a Lie group continuous symmetry transformation, the Lie group worth of symmetries, then the generator, there will be conserved charge. There will be conserved current. The conserved current in the case of Poincare group is T mu nu. So what are the charges? Once you have the current, you integrate the gains on codimension 1 surfaces, right? And you get charges. So constant time slice surfaces, you get charges. If you integrate this on a constant time slice, so this is space dimensions, dd minus 1 of x. If you integrate theta of 0 mu, so what is theta of 0, 0? The 0, 0 component of stress tensor is, anyone? Energy density. The I component of it, I is a 1, 2, 3, is pressure. The IJ component of it has to do with shear, and the 0I component of it is momentum. Okay, well, it's energy flux. I shouldn't call it. Yeah, it's energy flux. It's not momentum. So here's energy flux. If I pick mu to be I, this is energy flux. Momentum flux, sorry, momentum flux. I integrate it on a constant time slice and I get momentum. So it's like momentum density, if you wish. If I pick this 0, 0, that's energy density, I integrate it, I get P0, which is Hamiltonian, which is energy. That's why theta 0, 0 is energy density. So I can write this in a covariant form in this way. M mu nu is, now this is the conserved current associated to translations. The conserved current associated to Lorentz transformations is this. I'm just plugging in literally the formula from we found from Noether's theorem in part 1 of the course. Here's the conserved current, conserved charge associated with Lorentz transformations, Lorentz symmetry. And you can see that well, we saw that Lorentz symmetry would require that theta mu nu is symmetric. So one interesting lesson here is that if you have translation invariance in space and time, but not Lorentz symmetry, you do have a stress tensor, but it need not be symmetric. We talked about that in part 1 of QFT. Now, what about the conformal charges? The conformal charges, well, you could calculate using Noether's theorem. You can calculate the current. Here's another current for scaling. And if you integrate that against on a constant time slice surface or some codimension one surface, this is the, I don't know if this notation is familiar. This is the normal to the surface, which is a vector. But if it's unfamiliar, just think of it this way. This is dilatation. This is the classical expression for dilatation. That's why we call the when we talked about the unitary, the general scaling, we wrote it as e to the power of I lambda d hat. D hat was supposed to be the quantum operator that acts like this classical generator. Right? Okay. Now, special conformal transformations. Similarly, we'll have a conserved current and conserved charge. Here's a conserved charge that you obtain, and these are called K mu. So it's a vector. It's a space-time vector worth of charges, right? So you had P mu, here's K mu, there's M mu nu, and then there's D. For those of you guys who are curious, it's pretty straightforward from here to see how you could package P mu. So mu runs from 0 to D. Oh, sorry, D minus 1. P mu, you have P mu, K mu, D, and M mu nu. It's easy to repackage this to show that why the conformal group is SOD, 2. All right. Questions? Or at least the Lie algebra is the same as the Lie algebra of SOD, 2. All right. Now, well, we defined the charges, but let's see what the consequences of conservation laws are. So we define this charge, P mu. This is momentum. In time direction, it would be Hamiltonian. It has to be invariant under time evolution. So P mu dot, if dot is d dt, and the decomposition of space into space-time into space constant time surface and dt time. This is del mu of theta alpha mu. So if this guy is 0, then P mu dot will vanish. Well, it's pretty straightforward to see that. Well, this is a consequence of translation symmetry, right? Sometimes people, well, let me write it this way. So stress tensor will satisfy the following relation. This is a consequence of translation symmetry. Scale invariance, if you calculate d mu of t dot, you find that scale invariance will require this to vanish, right? The integrand will have to vanish. But if you take derivatives from using translation invariance, you can see that this will vanish. A translation invariant, the scale invariant, will have to have a stress tensor that's traceless. So tracelessness follows. Check this step. It's just one line of algebra. Now, if there are, so now we define K mu, which is special conformal transformation charge. The derivative of this will take this form. Now, if there are theories that are scale invariant, translation invariant, And if they're still invariant, translation invariant, but not conformal invariant, we'll have to have a non-vanishing term here, classically speaking. All right, so let's see what happens. Scale invariance will tell you that this term will vanish, so this goes away. Lorentz invariance tells you that theta mu lambda will have to be symmetric. So the conserved current for K mu dot the conservation law of K mu is classically is applied is implied by scale invariance and relativistic symmetry. Well, this is not quite scale invariance because translation invariance was used to derive scale invariance here. So translation invariant, scale invariant theory has this term vanishes for it. If you are relativistic, this term also vanishes. So classically, based on this crude argument, we should expect that Lorentz symmetry and scale invariance will imply the full conformal group. K mu is also symmetry. Questions? I encourage you guys to think about why this is the case. But it's a pretty important, well, all right. Good. It's a natural stopping point to ask questions. Now, let's switch gears a little bit, and talk about the modern view of quantum field theory. Most of what I say here is going to be, well, actually, yeah, is going to be important in the course of this talk, in the course of this course, and we'll come back to these ideas over and over again. Consider a Lagrangian density, say a free massless scalar field, and then an interaction term. I'm going to call that the deformation term because I'm imagining this term is small. This somehow is small compared to this because we're going to do perturbation theory. That's why we call this deformation. So we have in our mind that there's some sort of perturbation theory, Feynman diagram, picture, blah, blah, blah. So this term in some sense is small compared to this. We talked about what in one sense it is. It is integrated action, integrated over space-time. Action should be smaller than this term. We talked about that in part 1 of the course, but it doesn't matter. So this is, I'm going to call this deformation on the interaction term. This term is classically invariant, and this term will, whether it's invariant or not, will depend on the dimensionality of G. So when the dimensionality of G is D minus O, when G has no scale dimensions, we call that a marginal scaling, marginal deformation. It does not flow under scaling. It's invariant under scaling. When G has positive scaling dimensions, under scaling, we call this a relevant deformation. Under scaling, this grows. This term grows. When G has a negative scaling dimension, we call that irrelevant, and under scaling, it decays. So one obvious example is, what is the simplest term I can add here to any theory? Mass term, right? The coupling of this mass deformation is mass squared. So its dimensionality is always 2, which is relevant. So mass is a relevant deformation always in any theory, which means that it grows in the IR. Mass grows in the IR. We're going to discuss it in absolute detail. Now, recall from lecture 1 that we talked about superficial degree of divergence, and that was also related to the dimensionality of the coupling. We said that when G has dimensionless, this is related to renormalizable theories, at least superficially. When G has positive dimension, these are super renormalizable theories. These are nice theories. And G is negative, these are non-renormalizable theories. These are theories that are going to give us a hard time. So let's think about this a little bit. When G is positive, has positive dimension, is when G is relevant, it grows in the infrared, which means that in the UV, it is small. It decays in the UV. And as you go deep in the UV, these terms are suppressed. When we are doing calculations in Feynman diagrams in the loops, they will not give us a hard time. They will not give us divergences because the divergences come from the UV and the coupling is smaller and smaller in the UV. These theories are super renormalizable. They are their divergences are very mild and could be taken care of. We said that superficially super renormalizable theories are theories, or actually super renormalizable theories are theories that only a finite number of amplitudes diverge. When it's marginal, the coupling in principle does not change under scaling. Classically does not change under scaling. Now, quantum mechanically could change, which could become marginally relevant or marginally irrelevant. We're going to discuss all of these later. But this has to do with renormalizability. These theories will have a stronger form of divergence than super normalizable theories, but still under control. They show the behavior that, at least superficially, they show the behavior that a finite number of amplitudes diverge. Now, non-renormalizable theories are theories that have couplings that are irrelevant. Irrelevant couplings decay in the IR, which means that they grow in the UV. In the UV, they are big. So in the loop integrals, your couplings, your interactions in the loop at at very high energies become more and more important, which makes the divergence of your interactions much worse. The divergences due to your interactions in your Feynman diagram much worse. These are non-renormalizable theories. These are the theories that basically all sorts of divergences appear, and often they are well, we're going to talk about that hopefully as effective field theories, but they are not renormalizable. There is a little comment here that it's possible that symmetries intervene and forbid the certain behavior, decay. For example, the decaying term, this is the generic behavior, but the decaying term, the coefficient of it might be 0 because of some symmetry. We're going to talk about the connection between renormalization symmetries. Sometimes when people talk about standard model of particle physics or phenomenology of quantum field theory, they talk about operator dimension, right? They talk about terms in the Lagrangian that have operators of dimension such and such. This is the physics of it, right? It's about whether it's relevant, marginal, irrelevant. All right, any questions? This slide plays a very, very important role in this whole course. So in this modern picture, the whole perturbation theory is viewed as perturbation theory around free massless quantum field theory, which is scale invariant. And any interaction term, whatever it may be, its behavior is really split into these three possibilities depending on the dimensionality of the coupling, right? It's either relevant, marginal, or irrelevant. Irrelevant is bad, marginal is okay, relevant is great from the point of view of divergences in UV. Questions? Now, the modern perspective is the following. If we have a way of systematically studying scale invariant theories, which are not free field theories, free massless field theories, there are theories that are conformally invariant, then any such theory could be taken as the starting point of a perturbation theory. Because all the data of this theory is fixed the same way that the data of this theory is fixed. Somehow we have a way of solving for it. This is the Gaussian theory. We've solved it exactly. Even the mass term is also Gaussian, but it doesn't matter. And the CFTs, the symmetry group is so large that we could build examples of non-free conformal field theories, and we know everything about those correlators, about their physics. Now, once we have such a theory, we could take the starting point of perturbation theory and then deform it by small deformation term, which is some operator, some term like this in Lagrangian. Now, all that matters is that the scaling dimension of this guy, say is delta, will tell you that the scaling dimension of G, the coupling, is D minus delta. Now, depending on what delta is, you're going to have an irrelevant deformation, marginal deformation, and a relevant deformation. Any CFT, as we just described, will have a dilatation from Wigner's theorem, will have a dilatation operator and dilatation generator action that acts like this. So when we study CFTs, conformal field theories, the goal is to classify all the scaling operators, all the operators that satisfy this equation, and make a list of deltas. Now, those deltas will tell you what are the deformations you're allowed to have. You could take your CFT, deform it by adding this term, and it will flow. In the infrared, if the term that you pick is marginal, it's possible that you end up with an exact CFT. You're going to get a line of CFTs. If it's a relevant deformation, delta is between 0 and D, then it's going to grow in the infrared. You're going to get some quantum field theory that's massive. And when it's irrelevant, well, it will ruin your UV, and the perturbation theory is not well posed. This formulation, this modern way of thinking about stuff, is called conformal perturbation. So, sorry, this allows you to define a quantum field theory perturbatively as a perturbation theory around the CFT. Now, everything we've talked about in this Lagrangian formulation of quantum field theory is about perturbation theory around a very trivial CFT, which is the massless free scalar field, right? So what this conformal perturbation theory does for you, it gives you a definition of quantum field theory in a more general setup. Our modern understanding of quantum field theory is a CFT that is deformed by some relevant operator. This is our modern understanding, or if you wish, working definition of what quantum field theory is in the community these days. Questions? By the way, the scaling dimension has to be non-negative. It has to be positive. That's a consequence of unitarity, but I'm not teaching you CFTs. So hopefully this will give you some motivation to go and to study conformal field theories and try to classify them. This is a program that's been successful in 1+1 dimensions with some conditions. Questions? All right. If there are no questions, now I'm gonna start the discussion of renormalized perturbation theory. Well, actually, maybe make it. I'm gonna make a longer pause because renormalized perturbation theory is what we're gonna talk about for the next lecture as well. So I want to make sure that there's a little bit of a change of gears. Questions? I encourage you guys to think about this. This is really the language that has completely dominated our understanding of quantum field theory these days in high energy physics and condensed matter theory, actually. All right. Renormalized perturbation theory. All right. What I'm going to say today, in this 20-something minutes that I have, 25 minutes that I have, is trying really hard to simplify the principle. There's a very, very simple principle at work. If you pay attention and get this principle, a lot of the calculations that we'll do later in this course will make sense. If you miss this step, it might be hard to keep track of all these integrals and divergences and cancellations. The principle is always come back and look at these slides or this part of the very definition of the idea behind renormalized perturbation theory. I'll try to repeat the idea several times throughout the course. Renormalized perturbation theory is the way we make sense of, the physicist way we make sense of divergences in quantum field theory, perturbation theory of QFT. That's how we make sense of it. It is a little bit dirty, like dirty as in like mathematically not the most rigorous thing to do, but well, it's physicists have built this. So let's see how it works. And there are all sorts of things that we are going to say that later on, if you continue studying exact RG, you learn that we're special to this context. There's a lot of interesting stuff, simplicities that occurs because we're in perturbation theory around a UV fixed point. All right. When consider CFT Lagrangian, which is a free massless fields. For the rest of this course, we're gonna come back to perturbing free massless theory. So it's trivial CFT. Every time I say it's trivial CFT, that's what I mean, right? We start with the bare Lagrangian. This is lambda phi 4 theory, right? So the deformation terms are these two. The dimension in 4 space-time dimensions, this has dimension 2. It's relevant. In arbitrary space-time, it has dimension 2 and it's relevant. In 4 space-time dimensions, this is dimensionless. Lambda naught. So this is a classical marginal deformation. All right. Phi naught is what we're going to put in the Lagrangian. So we're going to define a Lagrangian for m naught, lambda naught, and phi naught. These are bare variables. They are unphysical. Let's just start with this action, keeping track of them. Now, define new variables. MR, renormalized mass, lambda R, renormalized coupling, and renormalized field. And some renormalized Lagrangian, plus something we're going to call counter terms. So we're going to split this term, this action, this Lagrangian density into 2 terms, right? MR, lambda R, and phi R are going to be renormalized variables. These are physical observables, and phi naught, lambda naught, and m naught are going to be unphysical. There are divergences here. There are divergences here. The idea is that counter terms are going to capture the divergences that we encountered in perturbation theory in an organized and systematic way. Questions? So we take our perturbation theory Lagrangian that we had started with, split it into 2 terms. The a term or a Lagrangian that's in terms of the renormalized variables and the counter term. There are infinities here, there are infinities here, there are no infinities here. That's the whole point. So I'm intentionally putting R on renormalized to remember that these are renormalized variables, but some textbooks like Pesky and Schroeder, they write the renormalized variables that without any m and lambda, because these are the physical variables, and then keep the zeros here. Because I don't want you guys to get confused about it, I'll try to keep the little r for as long as possible, but at some point I might just drop it because it's pretty annoying. That's basically what I was going to say. All right. So the bare Lagrangian, we're writing it as renormalized Lagrangian plus counter terms. the point is that the counter terms have to be local. Remember the principle of locality. The principle of locality tells you that your action should be written, you should be able to write it as an integral over kernel, which is a kernel in space-time, local in space-time. So if L naught is local in space-time, you want the renormalized action to also be localized in space-time, which means that the counter term should be localized in space-time. They're divergent terms, but they are still local terms. That's very, very crucial, right? We're insisting on locality. Consider a Feynman diagram with a superficial degree of divergence, capital D. So that means that schematically, it involves an integral, which is dk, k to the power of d minus 1, with a bunch of other stuff. For example, if you have a vacuum polarization, this vacuum polarization in these spatial dimensions is d to the power of dk, 1 over k squared, that has to do with this propagator, and then 1 over q minus k squared, that has to do with this propagator. Now, if you take derivative del q from this expression, it's clear that the superficial degree of divergence will go down by 1. Every diagram like this, of course, the internal variables are integrated over. So it's a function of q, right? Now, you could expand it as a polynomial in q, and then you could ask about where are the divergences in terms of the coefficient of this polynomial. When you take del q, you're looking at the next term down in the parallel, in the polynomial. If you take d plus 1 derivatives, we get something convergent, right? It's pretty clear for these kind of expressions that if you take, every time you take a derivative with respect to q, the degree of divergence comes down by 1. So if you had degree of divergence d and you took d plus 1 derivatives, you get something convergent. So another way of saying that schematically is that this diagram, a diagram with superficial degree of divergence d, is expected to look like a polynomial. This, do not confuse it with p momentum. Some polynomial of degree d in q plus a piece that's finite. This is some function of q that's finite. So let's do a toy example. Consider this integral. These are not coming from necessarily from any particular Feynman diagrams, but I just want to tell you the structure mathematically what we're doing in simple examples to get used to it. Consider an integral which I'm going to call I naught of q. It's integral from 0 to infinity of dk over k plus q. This has superficial degree of divergence 0. Right? Now, if you take a derivative with respect to q, you're going to get this. Now you could perform the integral and get minus 1 over q. This integral is somewhat subtle, but this is the answer for it, and it's finite. This suggests that if the derivative with respect to q is minus 1 over q, this suggests that I0 of q was a constant minus log of q, right? Now, this is finite, and this is constant. This constant is where all the divergences of this term have gone. This is a polynomial of degree 0 in q that is divergent. Right? So these are where the divergences are. D is 0, so it's just a constant term. The finite piece is minus log of q. And they found the finite piece by first taking a derivative with respect to q, taking the integral, and then integrating it out. There will be a constant term. All the divergences are in that term. Questions? Toy example 2. Imagine the following integral. I'm going to call I1 of q. 0 to infinity dk, k over k plus q. you can hopefully see why I'm doing these. I'm considering these kind of terms, right? These kind of terms appear all over the place in Feynman diagrams, right? Terms like this, for example, can come from well, propagators, but loop integrals with fermions, for instance. So we're going to consider a diagram with superficial degree of divergence 1. Our integral with superficial degree of divergence 1. This is the previous integral with a k inserted in the integrand. So it's dk, k over k plus 0, q. Now, if I take a derivative with respect to q, I'm going to get minus k over k plus q squared that I can write as minus I naught of q minus q I naught prime of q. This is just one line of algebra. You can convince yourself of. But we just calculated I naught of q. So there is a divergent term which is constant, minus log of q. So that's this term. Minus q I naught of q, I naught as I0 prime of q. And we also calculate that too. So if you just plug them in, you'll find that this is a log ln of q plus constant. You integrate again, you're going to get I1 of q is a plus bq plus q log q. Sorry. Here are the divergent terms, and this is the finite piece. This was an integral superficial degree of divergence 1. So the divergent terms are packaged in a polynomial degree 1 in q. A and b are both divergent. And the finite piece we extract is q log q. This is the principle, right? This is the principle is what I said up here, and I'm giving examples of how it works. Once again, we're being physicists in this part of the course. All right. Now, to see this principle work, let's go back to the lambda phi 4 theory. Let me see. Yeah, let's go back to the lambda phi 4 theory in D. I just want to put the zeros so that you guys remember that this is bare. Consider the bare Lagrangian in space-time dimension 3 plus 1. And here's the bare Lagrangian with all bare variables. The superficial degree of divergence, D, is 4 minus n phi, the number of external legs. Do you remember how this worked? When we talked about the superficial degree of divergence for free scalar for lambda phi 4 theory, we saw that it only depended on the number of external legs, right? And in 4 dimensions, this is what it is. So for the phi 4 theory has a special case that the term that was a coefficient of v, number of vertices, vanishes. And then in 4 space-time dimensions, this is the point we obtain. So the divergences are in the 0-point, 2-point function, and 4-point functions. 1-point function and 3-point functions vanish. Hopefully you remember, this has to do with the Z2 symmetry, which is phi 0 going to minus phi 0. So those are the only terms, the only diagrams we have to consider. All right, here they are. Here's a 2-point function, here's a 4-point function. Based on the discussion that we just had, because the structure of the divergences, first, we saw that the theory has a special property that the structure of the divergences only depends on the external legs. It means that this is a sum of all sorts of Feynman diagrams. But each Feynman diagram is expected to diverge like this, just based on the arguments we've had, which is a plus bq squared. This is a polynomial of degree 2 that captures all the divergences, plus a finite term. The 4-point function will have a constant piece that's captures the divergences, and then a finite piece. You see that there's no q term. Is it clear why? Well, for one thing, there is no q. There's q mu. This is the external the external momentum. There can't be q mu because that's not Lorentz invariant. So it has to be contracted. So q squared is really the only option. You can convince yourself of that too. This is a function of q squared, actually. all the divergences. So this simple argument tells you that in lambda phi 4 in d equal 4 dimensions, all the divergences you're going to encounter are expected to be captured by three divergent terms, A, B, and C. This is associated with phi squared term in the Lagrangian. This is associated with del phi squared. This term is like the two-point function of del phi squared. Every del brings down a cube. And C is associated with phi 4 in lambda in this. These are all the divergences we're going to encounter in Feynman diagrams of this theory, in amplitudes of this theory. Questions? You see the power of all these dimension counting that we talked about. All right. Here is where the magic happens. Let me see. Well, I'm going to say it and I'm going to repeat it next time as well. And I'm going to repeat it a couple of more times. So what is the renormalized field? The renormalized field is defined to be the unrenormalized field, phi 0, the bare field, multiplied by some constant z to the power of half. That's going to be infinite, actually. But it's different by some z to the power of half. This number, because they have the same dimension, right? This is a dimensionless number. We're going to keep track of this. So take your free Lagrangian and just plug in z for phi r in terms of phi naught. This is what you get. Next, what we want to do is we want the Lagrangian to look like the Lagrangian of the renormalized field with the renormalized mass and renormalized coupling. So we just write it as this term, and whatever is the difference. The difference is just like this term, subtracted from this minus this plus this, that I've written this way. So this is just an equality. It's just a repackaging of the initial action. I started with the Lagrangian of the bare Lagrangian in terms of bare parameters. I introduce a renormalized field and some renormalization value z half. Using that, I rewrote my same Lagrangian as this plus a bunch of new terms. These are what we call the counter terms. So this is the counter term for A, because it has a q squared, remember? So, yeah, sorry. This is the counter term for A, right? A has to do with phi squared. This is the counter term for B. It has to do with del phi squared. And this is the counter term for C, right? But now what does it look like? It looks like the bare theory has the same Feynman diagrams. Sorry, the bare theory looks like the same action for renormalized theory with a bunch of new interaction terms. These are new interaction terms, if you wish. So renormalized perturbation theory is taking this Lagrangian, writing it in terms of the renormalized variables, and then doing perturbation theory. Now there are new terms next to, so for your normal, wait a second. Yeah. So the first two, this part will give you this diagram for propagation of phi r. This will give you this vertex, which is renormalized, right? Well, let me not, yeah. Well, actually, yeah. It'll give you this diagram. But then there is this, which has to do with this counter term, right? This is a counter term for the propagator phi. There's a p squared, or I call it p squared here, but q squared term right? And then there's the order 1 term. And then there is a counter term for the C term. So this is the counter term for A, B term, and C term. This is that function that captures divergences, right? All the divergences are captured in this. So all we're gonna do now is we're gonna take this action and do perturbation theory with these new Feynman rules. We have 2 new terms. This one is for the propagator. This is the counter term for the propagator, and this is the counter term for the Lagrange. You just draw your diagrams and include all these guys as well as your normal terms. Questions? Is this first step clear? What we did? We're repackaging the original perturbation theory in terms of some new variables at the cost of introducing new vertices and terms in the Feynman diagrams. New ingredients of Feynman diagrams that are called counter terms. Now we have renormalization conditions. Renormalization condition is the statement that, well, if what we're doing is correct, the 2-point function of the renormalized field in momentum basis should look like 1 over p squared minus mr squared plus terms that are finite. So when you look at the 2-point function of phi of r and tune p squared to be near mr squared, you should have this pole. So the full propagator with these Feynman rules should show this pole at the renormalized value plus a bunch of terms that are regular. This is the renormalization condition for the 2-point function. You also have a renormalization condition for the 4-point function. When you calculate this vertex, it should become minus I lambda r when s, so this is a function of s, t, and u. When s is 4 mr squared and t and u are 0, this should become minus I lambda r. I'll come back to this in a second. These are called renormalization conditions. I'm going to explain them a little bit more again, but I'm telling you in advance what they are. Questions? The reason that this renormalization condition is like this for this s equal 4 mr squared, these are the Mendelssohn variables, right? S, t, and u, is that when you look at the 4-point function, at one loop, you have this vertex plus, these are the contributions of one loop. You also have the vertex, the new term, which is the counter term for this guy. You have to add these terms. Now, if you look at this term, this we calculated it in part 1 of the course is minus I some function of q squared. Now, because this is a function, the symmetry of these diagrams tell you that if this is v of q squared, then this is going to be minus at one loop minus I lambda of r, this guy, minus I v of s, because this is the s channel, v of t, this is the t channel, this is v of u, this is the u channel, minus I delta of lambda, this is the vertex for the at one loop. So at one loop, this is our the result of our perturbation theory, renormalized perturbation theory. Good. So now the renormalization condition is clear. If you set t equals 0 and u equals 0 and s equals 4m squared, then you're expected to get the renormalized. This is renormalized. I'm not putting the r anymore. You're supposed to get the renormalized action. Good. Which immediately tells you that because this should hold, this at the value of s equal form squared, t equals 0, u equals 0 has to be minus I lambda of r. It tells you that these two terms will have to cancel at this point, right? So we obtain v of 4m squared plus v of 0 plus v of 0 should be equal to minus delta of lambda. That fixes for you the counter term. So the job of the renormalization condition is to fix the counter term. Once we fix the counter term, then the vertex at an arbitrary external momenta is what you know the value of the delta of lambda from this equation. You plug it in, and for arbitrary s, t, and u, you know what the vertex is. Questions? Oh, I'm running out of time, so I'll probably stop here. Are there any questions? I'm going to review this next time as well, but it's important. So let me summarize one last time. This so far, the renormalized perturbation theory is the following idea. You start with your good old perturbation theory, Lagrangian. You put a 0 or next to every variable, your couplings and the field. These are the bare parameters. They're unphysical. Then you define a physical field or a renormalized field, which is related to the unrenormalized one, bare one, by some variable z to the power of half. Then you rewrite your action. We're still dealing with the action of the initial action that we had, which was with all the bare things. But once you write this in terms of the renormalized theory, with the action for the renormalized theory, you end up with a new terms and new terms that will contribute to Feynman diagrams. These are the terms that carry the divergences, capture the divergences. These are what we call counter terms, right? We did this explicitly for lambda phi 4, and the idea is that the renormalization condition will fix for you the values of counter terms. Once the counter terms are fixed, these are infinities, right? But they're formally fixed. You have renormalized your theory at certain scale. You could calculate how things change as a function of scale. All right, I'm going to stop here. Are there any last questions? We're going to do this and redo this and redo this a couple of times in this course so that you get comfortable.
Professor, I missed some point. How do we get the renormalization condition at first?
Renormalization condition is a physical requirement. What is the point of introducing phi r, right? Phi r, I just called it renormalized, and I say it's physical. What does it mean that it's physical? It means that it's related to something that we observe. What is that thing that we observe? What we observe is that the physical field, when it propagates, it has the physical pole as a physical mass. What we observe that's physical is that when the physical field scatters, the coupling is the physical coupling. So we have to somehow implement that condition somewhere in our equations, because here it's just I'm going to introduce some arbitrary z, some arbitrary phi of r. Right?
Yeah.
The normalization condition tells you what is this physical observable that you have and puts it in. So it's the input from experiments.
Okay.
We're going to discuss this in more detail. But it's very, very crucial. Any other questions? All right. If not, thank you so much, guys. And I'll see you guys on Tuesday. Please do think about what you want to see in this course. All right. Have a good evening, guys.